Okay, so we're going to continue on with the kinetics here. And what we're looking for is, in the observations, we're looking for patterns. So one type of pattern, as I was saying last time, is when things decay linearly. Let me see, is this going to work today? Yes. So it's just a straight line decay here. That is, the concentration decreases linearly with time. Another type of decay is the first order decay, like this, where the concentration decreases non-linearly. And the way it behaves is like, if we start off with 1, the whole amount, we go to about half the amount in about t, and then if we go from 1/2 to 1/4 of the amount, that is half the next amount, then that's going to take the same amount of time here. And so we call that T1/2. And each successive time we cut this concentration in half, so we'll cut it in half again, it's going to take the same amount of time, T1/2. We could also do the T1/2 analysis over here. On a linear one, the T1/2 gets cut in half, so maybe this doesn't look so accurately drawn, but okay, we cut it in half here, and then we cut it in half again, although this is not drawn very well. It takes half as long, and so the T1/2 is getting shorter here. We're just looking for patterns right now, but here T1/2 shortens. Over here, T1/2 is constant. And then we have another type of pattern that you should be able to recognize, and that's going to be a second order. And so when we look at second order, it's also non-linear, but the way it decays is a little slower. So if it takes T1/2 here to get halfway, let's say this is about halfway, and so that's the time it takes 1/2 of it to get consumed, the half-life. Then the next half-life actually is going to take twice as long, and that would be second order. And so if we double that, it would place the next point out here. So it's a slower decay, or more gradual decay, versus a first order would be a faster decay. So this is T1/2. The second T1/2 is twice as long as the original T1/2. And so maybe I'll put that here. Second T1/2 equals 2 times original T1/2. And so we'll just say previous. And so each one takes twice as long as the previous one. Okay, so that's first order and a second order type curve. And linear is called zero order. And so I'll just write that here, zero order. But there are other patterns here, but these are the 3 we focus on here. Now, that's the pattern in the half-lives, T1/2. But we also see a pattern in terms of the rates here, or the slope. And so the rate or the slope also shows a pattern too. And the rate of the slope is going to look like this. So for zero order, the slope doesn't change. Actually, let me try to draw it more accurately. So let's say this is the first half-life. The second half-life is going to be half as long as the first half-life. And so the first half-life takes this long, so we'll go about this long for the second half-life. And that would be here. And so this would be linear. But what we see is that the slope stays constant. That is, the rate is, in this case, equal to, the absolute value of the delta of the concentration over delta T, and that's equal to the negative of the slope because we want to make sure that the rate stays positive, so that's the negative of the slope. And the slope here is just equal to delta y over delta x, which is this right here. Okay, this is a constant. However, what happens when the rate is changing? And so let's take a look at the first order type equation here. And let's take a look at what's happening with the slope. So I have my initial point here. First order, the way I usually draw it is go about halfway, and then we have our first data point, and then cut this in half again, and that should take the same amount of time. So if we cut that in half again, and we go out to about the same amount of time here, be here, and then again we cut this in half again, and we go out the same amount of time, about here. Okay, and so here is our first order curve here. It's kind of hard to draw. This shouldn't be this little upward till it should go down. So let me try to draw that again. It's curved, but it's hard to freehand the curve here. Alright, now if we zoom in and we take a look at the slope, let me try to zoom in here. The slope, what's happening is the slope is constantly changing on this curve. So initially the slope is, let's say, this. And then we see the slope gets cut like this. And then the slope gets cut like this. And then gradually gets less and less steep. So an interesting thing happens. The rate or the slope, okay, let's do this. This will be the instantaneous rate in this case. Is going to be the slope of the tangent line, which is this is going to be the slope, which is delta of the concentration over delta t, concentration of whatever we're monitoring over time t. And that slope is changing. That changes with the concentration. If I cut the concentration in half, what happens to the slope? It turns out if I cut the concentration in half, the rate gets cut in half. And so we have this, it's equal to some kind of constant, which we'll call K is a constant. And it depends on the concentration here. Concentration, like this. And it's going to depend on the concentration directly. That is, the concentration to the first power. And therefore, this is why we call it first order. It's dependent on the concentration to the first order. That is, if we cut the concentration in half, then the rate gets cut in half. And so what we're going to see is that if we have our initial rate here, we'll call it just rate 0, then this one will be 1/2 because the concentration is 1/2 that, and so this will be 1/2 rate 0, and so on. This would be 1/2 rate 2, or 1/4 rate 0, and so it's directly proportional to the concentration times this constant. So if we double the concentration, the rate should double. If we triple the concentration, the rate should triple. But if we cut the concentration by some factor, then the rate should be cut by that particular factor. This rate constant is different for different things, and so we're going to use the same symbol up here for this constant, which is just K. That's our constant here, but this K is different, than this K. The units are different here. In this K, the units would be in terms of molar, which would be the change in concentration, over time. Time could be seconds or minutes or whatever. And then let's see. Then if we go over here, this constant already has molar on the top. So this would be like 1 over, the units would be 1 over seconds or minutes or whatever units you're using, hours or whatever here. All right, so that's a pattern in the slopes here. When we take a look at the next one here, for this was what we call the first order. And then we're going to have second order here. For second order, what we're going to have is a situation where, okay, as far as the half-life goes, okay, let's cut it in half here. It's going to take T1 half to get there. But when we cut it in half again, it's going to take 2 times the original T1 half, which brings it out here. And then if we cut it in half again, then it's going to take double the previous half-life, which would be this one here. So if we doubled that one, it would take it all the way out, just eyeballing it out to here. Okay, when we see this kind of decay pattern, this is a second order type decay in the concentration that we're seeing here. So here's the concentration versus time. Now, what's happening with the rate of the reaction here? What's happening with the rate of the reaction here is, okay, let's start off with our initial rate here, right at time 0. And then when we cut the concentration in half, what happens? Well, you know, this one slows down more rapidly than the previous one. And so when we look at the relationship, the mathematical relationship, let's take a look at the instantaneous rate again here. Instantaneous rate, which is going to equal the delta concentration over delta T. This one is going to have an interesting dependence. It's going to depend on K, and then it's going to depend on the concentration. So if we cut the concentration in half, the rate actually slows down more significantly. And so what we see here is a squared dependence, hence second order here, dependence on the concentration. So if the concentration gets cut in half, then 1/2 squared is 1/4. So this is actually 1/4 of the original rate. And so let's say this is rate at time 0 here. This is rate at 0, and then the rate at this first half-life is going to be 1/4 that. And so the rate here is just going to be 1/4 the original rate because of the way it decays, like this curve. And so we're going to look at the mathematics of this. In fact, we're also going to look at the mathematics of the T1 half. You know, empirically, T1 half is just this, but we're going to do some calculations. Now, when we do some calculations, the first one we're going to do is, okay, these are just some basic empirical observations. But there are other observations here where we don't track this reaction progress. And so rather than tracking this reaction progress, what we're going to do is we're going to look at some generic reactions. We're going to come back to this. We will revisit this. And then what we're going to look at is some other patterns that we see, or other empirical type observations. So this is going to be for general reaction. For general reaction, let's go with AA plus BB plus CC yields product. what we're going to come up with is something called the rate law. The rate law is just some mathematical pattern that we might expect to see for this. The rate law is given as the rate. Now, this is, what is it the rate of? Is it the rate of consumption of A, or is it the rate of consumption of B, or rate of consumption of C? Well, this is going to be the normalized rate of reaction for this reaction. The normalized rate of reaction is going to just be 1 over A, so we're going to just normalize it here, times delta, the concentration of A over delta T. And then that would be 1 over B times delta B over delta T, etc. That way, you know, if A reacts twice as fast, then we're going to have like this normalization 1 over 2, you know, or if B reacts 3 times as fast, it's going to be normalized at 1 over 3, etc. So the rate of the reaction here, in terms of rate law, is just going to equal K. Now, this constant, you know, the units depend on the order of reaction. The bigger the K, the faster the reaction. The smaller the K, the slower the reaction. But the K we can get experimentally. Units depend on order. But on something called the overall order of reaction. Overall order of reaction. Which we'll talk about in just a sec here. And it's going to depend on the reactants. A, B, C, etc. However many reactants we have. And the products aren't going to be included in the rate law here. And so normally we would raise A to the little a power, but here we're going to raise it to M. And then B we're going to raise to N, and C we're going to raise to MnO. M, N, and O are the individual orders. So M is the order with respect to A. Order with respect to A. The concentration of A. N is the order with respect to the concentration of B, and O is the order with respect to the concentration of C. And the overall order of the reaction is we sum them up. And so this is equal to M plus N plus O plus however many reactants we have in there. And again, we aren't going to divide by products or anything else. Now, why isn't it A, B, and C? Well, that's something that the theory is going to have to explain to us for. M, N, and O are usually determined experimentally. M, N, O, etc. are determined experimentally. There are different methods we can use to determine M, N, and O, but one of the more common methods is the method of initial rates. Method of initial rates. You know, because the rates are always changing, you know, and the concentration changes, the rates change. Unless it's zero order, then it doesn't change. But first, second, etc., there could be other orders as well, but we aren't really going to look at those. So we'll just look at the initial rate. If you recall, the initial rate is either the instantaneous rate at time 0 or the average rate if less than 5% reaction has occurred. So instantaneous rate at t equals 0, or average rate right at the beginning of the reaction when less than 5% reaction has occurred. And so just you catch the data right at the beginning. This way we don't have to generate the whole curve. We're just looking at the initial rates. And so what we do, sorry, I don't know, it's an announcement. So this is what we do. What we do is, like, you do the reaction. Let's say I had a reaction like this. I had a reaction that is like 2A plus B yields product. Would be an example. And so what we'll do is we'll just have the initial concentration and the initial rate. And so the initial concentration we'll just put as A, and then B initial. And then we'll look at the rate. And the rate is just going to be measured. And so the strategy goes like this. Let's say we have 0.1 molar and 0.1 molar here, and then we measure a rate we'll call rate 1. And then what we'll try next is we'll try to double the A concentration. For example, we might go 0.2 molar, but keep the B concentration the same at 0.1 molar. So if we double A, then we can see what's going to happen. And the B concentration stays the same, so let's figure this out. So let's say what happens is when we double the A concentration, the rate 2 is 2 times the rate 1. And so in the methods of initial rates, we would do something like this. We would put the rate law of 2 in here. The rate law for 2 is going to be just the A concentration to the M, and the B concentration to the N, and this is going to be for 2 and 2. Okay, then what we'll do is we'll just divide this by the rate for 1, which is going to equal the A concentration for 1 to the M power, and the B concentration to the 1 for the N power. Now B1 and B2 are the same, and so those cancel out. So these cancel out here, like this. And that just leaves us with A. So when we look at A2 is 0.2. So this is going to equal 0.2 over 0.1 here, raised, so I'm going to raise the whole thing to the M power. And this is going to equal R2 over R1, but R2 is 2 times R1, and therefore the R1s cancel out as well, like that. And so we end up simplifying this. This is going to come out to 2 to the M is equal to 2. Therefore, you could take the natural log or whatever. I mean, I don't think we quite have to do that. But in case, you know, you would have to do that, we probably can just eyeball this. We could do this. We could take the ln of 2 to the M is equal to 2, and then bring the M to the front. So this is going to be M times the ln of 2 is equal to, actually we got to take the natural log of both sides. Sorry, so I need to take the ln of this side too. And then just divide that, and so M is equal to 1. We could have eyeballed that here, because 2 to the M is equal to 2, M must be equal to 1. And so this wasn't really necessary to do, but sometimes the numbers aren't so easy to see. And the orders aren't necessarily always going to be 0, 1, and 2. You could have other orders as well, you know, depending on what's going on with the reaction. And so this is what we got. And so if we figured out what M is, and the K is going to be the same. I forgot to include the K here by mistake, but the K is the same reaction, just different concentrations. So those K's cancel as well here. Okay, now that we figured out what M is, the next step is to figure out what N is. So we'll need a third experiment here. And so we don't have to measure the whole entire curve. We're just measuring the beginning part of this curve right here, not the whole thing. So we don't know how it's going to decay. But what we should do in this case is we should keep maybe A the same as 0.1. So in number 3, this is 1, 2, 3. In experiment 3, A doesn't change, but maybe we'll double B. So that comes out 0.2 molar here. And then let's say that R3 is equal to R1. In other words, the rate didn't change. So if that's the case, then what we see is that, okay, this is the math way. This is just the other way of doing it. Okay, so we already know that it's going to be first order in A. We determined it from the math over here. But if we double B and B doesn't impact the rate, then it's got to be to the 0th order, because we doubled the B concentration and yet nothing happened. It's got to be 0. Or on the other hand, we could double the B concentration, maybe the rate quadruples. If we double the B concentration and the rate quadruples, then it's 2nd order, because that would be 2 squared, which would be 4, which would result in quadrupling of the rate. Okay, so once we do this, then the last step, okay, so first we determine M and N based on the behavior here. So first determine M and N, then determine K. In order to determine K, we need the numbers here for the rates. So, and so we need the quantitative rates. Because when we go to experiment 1, like this, then K, just solving the rate law, is equal to the rate divided by the concentration of A. We said that this is the first order, and the concentration of B to the 0th order. B to the 0th order is just 1. So this is just rate over A1, and so this is going to be rate 1. All the K should come out the same because it's the same reaction, and so this K from data from 2 should be the same as the K from data from 1. So this is going to be rate 2 over, A to the first. B to the 0th is just 1. And then the third one, trial here, we'll get another K, which is going to be rate from 3 over, this is 1, this is 2, this is 3, to the first power here. And then we're going to determine K average. Since all three should match, and hopefully they do, but sometimes there's going to be fluctuations, of course, in the experimental data, so we should average it. So K average is just equal to the sum of the Ks over the count, how many you have. And so once we do that, then we have the complete rate law. The complete rate law would be that the rate is equal to K A, this is going to be K average, A to the first, and that would be the complete rate law. Now what we can do with the complete rate law is we can use to predict the rate at any concentration of A and B, at any concentration of A and B. And so the rate law is just to determine, how fast is it going to be reacting. Let's say I cut A and I cut B in half. How fast will the reaction proceed at that point? And so we can use the rate law to determine the rate at any concentration. However, there's more questions that we would like to get answered, and for example, how long? Other questions come up. This will be how kind of the rate, the velocity of the reaction. But the other questions will be, how long, how much time will it take? And then, or other things would be, what is the concentration? What is the concentration after a given time, t? Okay, and so these are questions that we'll ask. For these questions, the math becomes more complex, and so these are more complicated questions. The problem is the rate is constantly changing. If the rate, actually, for zero order, it's not bad. You can predict how long things are going to take. But for something like this, where the rate is constantly changing, how long is it going to take? If the rate were constant, it would be pretty easy to figure it out. Let's say if you're driving, to someplace, and the speed is constantly changing. It's hard to predict how long it's going to take. Let's say you're driving somewhere and you're slowing down at a non-linear rate. How long will it take you to get somewhere? And so to answer these questions, we need to use some calculus. And so, actually, this is not working now. So what I'm going to do is, since this is not working now, I'm going to cut the video here and I'll post another video later. Okay, thanks for watching.